Hello, everyone, and welcome to my lab. Are you ready to learn? Yeah! Are you ready to have some fun? Yeah! Well, let's get started then. In my lab, we do a lot of fun experiments, and we always obey the safety rules. I am sure you have noticed that I have my goggles on. It is the state law that when we do scientific experiments that we put our goggles on. And I'm a law-abiding citizen, so I have them on. Now I ask you to look at this blackboard that I have down here. I'm going to put on it a small amount of a solid, like so. And then I'm going to reach for a flask that has in it a clear and colorless liquid. And what I will do next is pour this liquid on top of the small amount of crystals that I put there already. Here we go. Let's see how tall I can make it go. Steady hand, and do it slowly. The liquid is a supersaturated solution of something we call sodium acetate. And the crystals I put at the bottom are sodium acetate. So they seeded the crystallization. That's pretty good, don't you think? Huh? Look at that. Look at that. Look at that. You think it's going to stay up? We'll see. We'll see. So that's the crystallization of sodium acetate from a supersaturated solution of sodium acetate. This is a glass beaker. The volume of this beaker, I want you to look at it. The volume of this beaker is 4 liters. So this is a 4-liter beaker. If you look at it right now, you just learned how big 4 liters is. And you cannot unlearn it. You may forget it. That's different. You think about that, all right? So this glass beaker, 4 liters in size, is empty except for air. So I'm going to put a magnet coated with Teflon right in there and turn the motor on. Can you see the magnet spin? Let's see. Can you see it spin now? As you look down at it, is it spinning in a clockwise direction or counterclockwise direction? You can't tell because you have a digital watch? Is that what I heard you say? As you look down at it, it's spinning in a clockwise direction. Now I ask you to do something we always do in science. I ask you to visualize the same magnet spinning in this direction, except instead of looking down at it, we're looking up at it. So visualize there's a ceiling fan up there moving in this direction. As you look up at it, this is a clockwise direction looking down. When you look up at it, what direction do you see? Counterclockwise. Okay, I'm a little confused about this. So let's try to sort out this confusion. I want everyone in my lab, you and I, stick your finger out like this, right? And I want everyone in the lab to rotate your finger in a clockwise direction. Hey, I said clockwise. What are you doing? I'm doing clockwise. Look, watch me. Watch me. I'm doing clockwise, right? Am I doing clockwise or not? Yes. And then as I turn around, what do you see? All right, you get the point? You always have to be careful about the vantage point that you have when you make observations so that you don't make confusing observations. Always validate the observations and try to make sense out of them. So now I'm going to add 3 different clear and colorless liquids into this 4-liter beaker. I increase the spinning a little bit here. Here's the first one, clear and colorless. Well, it is right there, a little cloudy, not as clear as it was before. I add the second one, and I get an increase in volume, which is very easy to observe. Then I add, let me increase spinning here. And you see what looks like a tornado. I hope that's the only tornado you'll ever see. I add the third liquid, and I get this beautiful dark color. What's the excitement about? You're not paying attention to me anymore. What, am I missing out on something? What? Look, the last time I looked at the color of the liquid in the beaker, it was deep blue, almost black. Tell me when to look. Shall I look right now? No? Right this second? I don't want to trip over anything. Right? No? Okay, tell me when to look, all right? Help me out a little bit. Right now? Shall I look right now? No. Right now. You sure? Yes? Right now. Every time I look at it, it's deep blue. Maybe you can help me better on this side, okay? Tell me when to look. Shall I look right now? Right now. You sure? I don't want to trip over anything. I look at it, it's deep blue every time I look at it. What's going on here? Right now. You sure? Right now. Yes? Absolutely sure? Every time I look at it, it's the same color. Okay, all right. Oh. Now I see what you are seeing. And what is it that you were doing that I was not doing? You were looking all the time, but I was looking all the time, too. You were looking all the time over here. I was looking all the time at you, right? So when you do anything worth doing in life, pay attention to it. Don't get distracted, right? Pay close attention and enjoy the beauty of chemical transformations like this one, which is a chemical oscillating reaction. You like this experiment? This is one of my very favorite experiments. It's one of about 50 known chemical oscillating reactions. And I'll tell you why it's one of my very favorite experiments. Because it was discovered by 2 high school teachers. And it's named after them. It's called the Briggs-Rauscher reaction. Briggs and Rauscher taught high school chemistry and physics in Northern California. And in 1973, published a paper describing this beautiful, captivating behavior that we have been witnessing here. We continue to witness it. A second reason it's special to me is because it took researchers, high-powered researchers, members of the National Academy of Sciences. It took them 9 years to figure out what's going on in here. So when we do scientific experiments, we always pay attention, we are vigilant, we learn how to deal with frustration, we're always patient, and we always ask questions and try to come up with answers to those questions. Now I'd like to ask you to welcome my longtime collaborator and friend, Dr. Rodney Schreiner. Rod? Rodney?
Hello, Bassam. It's a pleasure to be here on this 43rd anniversary of your presentations.
Thank you.
And normally what I would do for you on this occasion is to present to you a sample of the element whose atomic number is 43.
Well, it's 43, yes.
But unfortunately, I don't have a sample.
How come?
I can't get one. That element is technetium.
Yes.
And every last atom of technetium is unstable.
You mean it's radioactive? It decays?
It's radioactive, right. So I can't get any.
Oh.
But instead, I brought you a book called Radioactive.
Oh, cool.
And this book is a biography of the people who discovered radioactivity. Marie Curie and her husband Pierre. And it's a very unusual book in that it's not like most books with white pages and black print. This book, well, there's one. But this book has many pages that are very colorful, like this one.
Yeah, I see that.
In fact, most of the pages are very colorful. They're all works of art. The author of the book is an artist. And I want to show you a book, particular pages. Why don't you hold that for me while I get out my stand?
Rodney, isn't this the book that University of Wisconsin-Madison this year is using as the Go Big Read book?
Go Big Read, yes. Every one of the incoming students is receiving a copy of this book so that it can be used in various courses across disciplines. You know, history, interested in biography, science for radioactivity, and art for the artist who made it.
I like mixing science and art. It's very enriching.
I do too. So here, let me put the book in the stand, and I want to show you this page in particular. There are quite a few of these pages that are nearly all blue. And this is, the original of this page is what's called a cyanotype. That's like a photographic process, but instead of using silver, it uses other chemicals. And I want to show you how that works. So this process starts by mixing two chemicals together and making a solution. The solution is sort of yellowish in color. And you take a piece of white paper, like this one.
This is the cyanotype you're telling us about.
I'm telling you about the cyanotype, yes. And you coat the yellow paper with that solution, that yellow solution. So I painted some on here. I had to let it dry, so I did that ahead of time. So now it's dry on this. Those two chemicals react with each other when they're exposed to light, and they produce a blue pigment called Prussian blue. And that's what you see on these pages, is that blue from the Prussian blue pigment. That reaction is taking place right now all over the paper. If I want to create an image on the paper, then I need to keep the light off of the paper in certain spots. So to do that, I have made this mask, which is a piece of glass where the light can go through, and black letters and numbers where the light cannot go through. So what I'm going to do is place the coated paper with the yellow side up, exposed to the light, and then I will put the mask right on top of it. So now the light can get through the glass, and it can change the color of the paper, but it can't get through where the letters and numbers are, and so the paper will stay that way. But the light in this room is, you might find this surprising, not strong enough to do much of a change. It's very slow. So I'm going to speed it up by exposing it to ultraviolet light, which I will get from this ordinary black light thing, a lamp that you could buy in a poster shop for making, for illuminated glow-in-the-dark posters. Here, I'll turn it on, I hope. There. So you can see it's sort of bluish in color, but most of the light that comes from this is invisible. It's ultraviolet light. And that will make this reaction in the cyanotype go faster. So I'll put that over here. And the light is now being absorbed by the chemicals, and the reaction is taking place faster than it was before. And while that's going on, I want to show you something else about this book. It's on the cover. So one reason the cyanotypes are used in this book is because radioactivity was first explored using a photographic process, the absorption of ultraviolet or high energy radiation by chemicals that change because of the energy. Now I want to show you there's another process which is also used for detecting radiation, and that I'm going to simulate radiation again with another black light. And I'm going to shine it on the cover of the book. And the book will show you another way in which radiation, which is invisible, can be detected by the eye. Of course, it's very hard to see with all the bright lights on in the room, so I'm going to ask that the lights be turned off. And with the lights off, I think you can see what's happening. The cover of the book is absorbing the high energy light from the black light and re-emitting it as visible light. There's some white light or bluish light coming from the cover of the book and sort of a yellowish green as well. Now what I'm going to do is I'm going to turn off the black light. And the cover continues to glow. The places where it's glowing means that there's a phosphorescent coating on the cover of the book. And so that method had been used for detecting radiation that is invisible. Now, with the lights back on, we no longer detect radiation that way. We now do it electronically. We have electronic devices like this one. It's a Geiger counter, and it will show us the presence of radiation in several different ways. It has a little red light that flashes whenever it detects radiation. And it has a speaker in it that beeps whenever it detects radiation. And it has a meter on the front to show us how much radiation it's detecting. Now, you can hear it every now and then it beeps because there's radiation around us all the time. It comes from the sun, it comes from the earth, and it's there all the time. But there are some substances that produce a lot of radiation. And some of those are used in commercial products. I am wearing, at this time, a watch which was made in the 1930s. This watch has a glow-in-the-dark dial, so that when it's dark, I can tell what time it is. I can read the light that comes from the watch. The glow-in-the-dark is the same material as on the cover of this book, but the radiation doesn't come from a black light. It comes from a radioactive material, radium, that's also mixed in. And because it's radioactive, the Geiger counter will respond to it.
I hear it.
Yes, beep, 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 beep.
Yeah. So it's hot.
It's a hot watch, yes.
Yeah.
Very hot watch. Now, this radiation is not dangerous to me when I'm wearing the watch because my skin protects me. The radiation cannot get through the skin.
So it's safe for you.
It's safe for me.
How about for me?
Safe for you, too.
Oh, good.
But it's my watch.
All right, all right.
And radiation is used in other commercial products, too. It's used in the glazes of some pottery. This piece, also made in the 1930s, contains uranium. The uranium is not in there because it's radioactive, unlike the radium in the watch. It's there just to make this pottery orange. But it is radioactive. Now, the pot or this little pitcher is not dangerous to me either if I use it. It would be dangerous to me if I were to eat it. Radiation is dangerous when you get it inside your body. So uranium is no longer used in making orange glazes. It's no longer used in making glow-in-the-dark watches, not because it's dangerous for the people who use them, because it's dangerous for the people who make them, because they're the people who might inhale dust from the glaze before it's fired, or who might get some of this paint that's put on the dial. So now, let's see how my cyanotype is doing. I'll turn off the ultraviolet lamp and put it away and show you that
Very nice.
now there's still some yellow on here, and in the book you saw there wasn't any, but I can get that off simply by washing it. Just putting it in water, it'll dissolve away. So I think that's what I'm going to do. I'm going to go back in the lab and wash my print.
Thank you very much, Rod. Thank you. Now I'll move on and do an experiment using this piece of copper that's been sitting on the tripod. I'll move this out of the way so you can see it a little bit better. And what I want to do is heat this piece of copper using this Meeker burner. So I'm going to try to turn the gas on here. There we go. And see, there it is. I want this to be really, really hot. So I'm going to turn the gas all the way up. Look at the nice, shiny surface of copper. Look at it very carefully as now we heat the copper. And as we heat the copper, we begin to see maybe some changes. Are you seeing any change so far? What's happening? We see a green flame, right? That's from the copper that's being heated. But also you see what? The surface is changing color. The surface is getting darker, right? That's because the hot copper surface is reacting with the oxygen from the air and forming a layer of copper oxide. Copper oxide is what's being formed here. Let's heat this a little bit more, because next I want to do a very, very interesting experiment. I want this to be as dark as possible, so I need a nice coating of copper oxide on the surface. And it is happening almost all around. You see that, right? Right? So we've converted the copper into copper oxide. There's a thin layer that has deposited over there. And this is pretty hot enough right now. Now watch carefully what I'm going to do next, because I'm going to turn the burner off completely. Completely. And I don't want any flames or any sources of ignition, because I'm going to open this tank that has hydrogen gas in it. And I open the tank, and the hydrogen is flowing out, and I'm going to bathe the layer of copper oxide with hydrogen. There you see copper, copper oxide, copper, copper oxide, copper, copper oxide. We keep doing this. As the metal cools down, we will reach a stage where we can no longer do it, but so far, so good. We're still doing it, right? There's a lot of hydrogen up in the air, so there's another beautiful chemical transformation. And now it's cooling off, and you like that? And now I ask you to focus your attention on these plastic bottles that I have, that have in them screws placed inside each. They're not touching on the inside. I want to show you what it looks like on the inside. It looks like this. So there are two screws. They're separated by a distance of about 1 centimeter. There's a cork on top, and at the bottom there's a clear and colorless liquid. And what I want to do is an experiment using something that gives off sparks. It's called a Tesla coil. A Tesla coil, when I push the button, you'll hear the sound, but you can't see the spark. Let me see if I can try to show you the spark here. Here it is. I'm going to grab this scoopula. I'm going to hold it real tight, and then, can you see the spark now jump? Okay. All right. So what I'm going to do is touch one of the screws and see if I can make the spark jump across the gap that separates the two screws. We'll see what happens. You ready for this? Here we go. All right, there's one. There's two. Ready for the next one? 3. You ready for this? You sure you're ready? All right. You've been a wonderful audience. Thank you for coming and sharing the joy of doing science with me in my laboratory. And I want you all to try doing scientific experiments. Remember, no matter what you do them safely, but also remember that science is fun. Thank you all very much. Thank you. Thank you. Thank you.